So in the following section, we're going to be talking about some other non-idealities that you encounter in silicon process. Some of them will directly affect the transistors, others just affect things like leakage, for example, affect power consumption and how fast you can maybe switch something on and off, but not directly affect the transistors as far as our IV current characteristics. So one of the main non-idealities is we have leakage in our currents. So like our transistor, for example, so when we go into the cutoff region for a transistor, our ideal results say that there's zero current in cutoff. And then we have simulations that might show us something different. So the difference is the current doesn't actually go to zero in cutoff. And I've discussed this before. It does go down steeply on a log chart, but it doesn't hit zero. And so you do have some power consumption that you need to account for. So going through some of the main leakage sources that we have in our CMOS process. First one is sub-threshold conduction. So this is that the transistors, as you're increasing your gate voltage and your drain to source voltage, the transistors don't abruptly turn on and off, like go from zero current to all of a sudden they're conducting. They tend to turn on potentially on in some cases, linear scale for this main leakage source, drain to source voltage. It might be on a log scale, but it's not an absolute infinite slope. So this is the dominant source in most contemporary transistors. Another source is gate leakage. You can actually get tunneling through your gate dielectric. I've been talking about, when I talk about the gate of a transistor, I've been saying silicon dioxide, gate oxide. It turns out several process generations ago, as the gate dielectric kept getting thinner and thinner, we started getting significant amounts of leakage through the gate. And it got large enough that they actually went to different dielectric materials. And so nowadays in modern processes with the lowest, smallest transistors, you tend to not have gate oxide anymore. You have other more exotic dielectric materials being used in order to try and reduce that gate leakage by a larger factor. And then a third leakage source is junction leakage. Throughout all of our silicon process, we have PN junctions all over the place. We have the PN junctions between source and drain and the bulk or body of a transistor. We also have PN junctions between the well of an N well and the bulk material of the silicon substrate. And so those reverse bias PN junctions all conduct current as well. Going into more detail on some of our leakage sources, first we'll go through sub-threshold leakage. Sub-threshold leakage is actually exponential with your gate to source voltage, and it has a fairly complex equation, as you can see in the top line of IDS. Couple things to note is it's a function of VDS, as we have in the equation, as well as VGS, and then there's also a parameter N. This parameter is something that depends on the process technology that you're using. So various different decisions on how you use different materials and dope the materials and put them together can, typically it's in a range of 1.3 to 1.7, but it's something you need to figure out for any given process. And you can rewrite that equation relative to I off and also on a log scale with the equation below. I'm not going to go into the gory details. Just know that it is something you can model. It's very complex modeling. Usually you won't try to figure out these equations by hand. You'll have this modeling in a simulator like SPICE, and you'll just actually put your circuits together and figure out what leakage you get based on the SPICE simulations. Gate leakage is the second of the leakage parameters that I mentioned a couple slides ago. And this is where you have carriers tunneling through the gate oxides as the gate oxides become extremely thin. This happens, has been happening because as we scale down the transistor lengths from one process generation to the next over the last 40 years, we also scale the oxide thickness to be ever smaller and smaller in order to get the devices improving in speed. And if you look at the equation below, you can see it's a fairly complex equation of how the current through the gate is affected by both VDD and TOX, but suffice it to say it's exponentially sensitive to both your oxide thickness and VDD. So there's two other parameters in there, A and B. Those are constants that are based on your technology, process technology. And another note is that the leakage is going to be greater for electrons than it is for holes. So the NMOS transistors will leak more than PMOS transistors. If we look at the chart on the right there, you can see that as we've been scaling the TOX, the thickness of the oxide, down to smaller and smaller, we're getting higher and higher leakage. J sub G is current by unit area, so it's the current through the gate per unit area of the gate. And you can see that that's been going up pretty significantly since this is a log scale on the left-hand side. We went from, if you look at the far right part of each curve at 19 angstroms of T oxide thickness, you were maybe in the 10 to the minus 3 in your current density, and then you get to 6 angstroms, and if you were still at 1.8 volt, you'd be somewhere around 10 to the 6th. So you've gone 9 orders of magnitude difference in leakage just by changing your T oxide by about a factor of 3. So that's pretty significant. You can see that as they've been decreasing the oxide thickness, they've also been decreasing the VDD, the voltage that you use. That does offset your leakage a little bit, but you can see that it has a very small effect overall. Maybe instead of 10 to the 6th leakage, you're maybe down to 10 to the 5. So it it helped by about a factor of 10, but when you were going by 9 orders of magnitude, one factor of 10, it's not enough to totally offset you. So another thing to note that this leakage in the gate leakage was pretty negligible compared to all other factors, something that we almost didn't care about and almost couldn't measure in older processes where the oxide thickness was greater than 10 angstroms. But it's definitely become critically important for any process, 65 nanometers and below, just because of how the gate leakage compares to other leakage parameters in the process technology. It's starting to become something that is on the same order of magnitude and difficult to account for. So the third leakage effect that I mentioned in an earlier slide was junction leakage. So this is due to the reversed biased PN junctions that we have in the various different PN junctions on the process technology that we're using. So in this case, if you look at the diagram below, you can see we're using a P substrate, so we have PN junctions to the N plus diffusions for the NMOS device. Then we have an N well, so we get reverse bias junctions from the N well to the P substrate. And we have the P plus diffusions going to the PMOS device inside the N well, and so we get reverse bias junctions for those PN junctions as well. There are a couple different factors in the leakage. One factor is ordinary diode leakage, and you can find equations on that. The second is what is called band-to-band tunneling. And the third is gate-induced drain leakage. And I'll talk about each of these in the coming foils. For ordinary diode leakage, basically we have a reverse bias PN junction, and those have some leakage based on the equation below, where the diode current is equal to IS, which is the saturation current of that diode, and that's based on area and some other factors, times E to the VD, which is the voltage across the diode, over VT. VT is our thermal voltage, typically for silicon at room temperature, that's 25, 26 millivolts. That factor minus 1 times IS. So any significant negative diode voltage, you'll wind up getting ID equals negative IS. And IS depends on your process technology, your doping levels, the area of the perimeter and diffusion regions, and typically that value in more modern processes is on the order of 1 femtoampere per square micron, which is small enough that it's typically been negligible and not something that we need to account for. Now, the band-to-band tunneling effect, this is tunneling that is in effect across heavily doped PN junctions. So the most heavily doped PN junctions that we have in modern processes are P plus and N plus diffusions for our transistors. So, and this is especially true in the sidewall that occurs between the drain and the channel of the transistor. The reason for this is because in modern processes, there's something called halo doping that's used in the channel area in order to increase VT, so that we don't get as much, with a slightly higher VT, we don't get as much leakage current through the channel. But that higher doping that's caused by the halo doping causes this heavily doped PN junction to see this effect even more. So this increases that particular junction leakage to significant enough levels that it's something that we need to pay attention to. Below you'll see the equation for band-to-band tunneling current. I'm not going to go into the details of the derivation. It's not something that we typically will ever hand calculate. Again, it's something that you would try to put into your SPICE simulation models if you can. Just one thing to note is that a couple of the factors that are in this equation, several of them are related to the process technology and the doping levels, and some of them are X sub j is sidewall junction depth, so how deep your PN junction goes from the surface of the wafer or surface of where your channel is down into the silicon. E sub g is your bandgap voltage, and then the factors A and B are constants related to the process technology that you're using. So you need to kind of curve fit those depending on a particular process technology and testing of your transistors. And then the third junction leakage effect that I mentioned was gate-induced drain leakage. So this occurs due to having overlap between your gate and your drain. So as you're doing your processing, if the drain winds up going underneath the gate, which tends to happen as you, so when you implant the, for an NMOS device, you implant the N dopants into the silicon. As you try to get them to activate in the silicon, you have to heat the silicon up a little bit. This causes them to migrate a little bit, and so they're going to go not just vertical into the silicon, they're going to go horizontal underneath the gate a little bit. So you will get some overlap between your gate and your drain. Of course, this effect of gate-induced drain leakage is most pronounced when the drain is at VDD and the gate is at a negative voltage. So I don't just mean a negative voltage relative to the drain, because typically if you have your gate at typically your lowest voltage is ground, and in our modern processes the voltage difference between VDD and ground doesn't typically cause this gate-induced drain leakage to be significant enough to be a concern. However, there are some usage cases where people try to have gate voltages that go below ground, and this is done in order to try and reduce the normal leakage between your drain and source. But when you have your gate voltage go below ground, then you start getting this gate-induced drain leakage that offsets that and causes this to be at least a noticeable effect that has to be accounted for. So this effect will actually thwart some of the efforts to reduce the sub-threshold leakage by some usage cases where people were trying to use negative gate voltages to reduce their leakage, and then they saw increased leakage due to this effect. You have to be aware of this effect when you're trying to counteract other leakage effects. One additional non-ideality that we haven't talked about yet is the temperature sensitivity of NMOS and PMOS transistors. And that is that increasing the temperature of the material winds up reducing mobility of the material, and it also reduces VT. So the reduction in mobility causes the on current, the maximum on current that the transistor can sink or source, to decrease with temperature, and the reduction in VT winds up causing your I off value to increase with temperature. So as you increase temperature, it affects your current IDS, the current through your drain, relative to VGS. The slope of that curve winds up changing, and so you have to be aware of this to make sure that you operate in a temperature range that works for your product. Or at the very least, when you do your testing, you have to do your testing across temperature and make sure that your device functions across all the temperature ranges that you plan on having anybody use it when you sell your product. At this point, you might be saying, well, so what? Why did we go through all these non-idealities? So what if the transistors are non-ideal? They still behave like switches, which is true, switches with some amount of resistance to them. But all of these non-idealities do matter for a number of reasons. One is, what supply voltage do you choose? Because a certain level of voltage will cause certain non-idealities to break down at different points and cause different amounts of effect. The other thing is logical effort, which I haven't gone through yet, but we'll go through in future weeks. Third one, quiescent power consumption, which quiescent means when you're not doing anything. So we have all the clocks turned off. We're not doing anything, trying to calculate anything. We're not using the device. If we still have the voltage connected to the device, all of these leakage parameters will actually consume power. And frankly, especially in like mobile devices, you don't want that. If you have your mobile device turned off and not doing anything, you don't want your battery to run dead in like 5 hours. You want it to last for days if you're not doing anything. So you need to make sure to reduce those leakage parameters as much as possible. And then of course your pass transistors are going to behave differently, so where and when you can use those. And then finally, as I mentioned in the previous foil, temperature of operation. You need to make sure that if you're going to be operating in an automobile, you might have to be able to operate down to minus 20 degrees and up to plus 140 or above that. And depending on if you're operating in the desert in the middle of the noonday sun. So you need to make sure to consider all of these along with your non-idealities as well as your optimal device parameter behavior. So one final topic that I'm going to discuss in the next few foils in this presentation is process variation. So as we are processing our silicon wafer and creating our IC chips, we will see some variation in transistors. And not just transistors, but also the metal layers. But right here I'm going to be talking about transistors. So there will be some amount of uncertainty for any particular transistor on what some of the actual process and parameters are. So for example, your L effective or effective gate length of a transistor could have variation on it. The threshold voltage can also have some variation on it, and the oxide thickness of a given transistor can vary as well. Now these variations will typically vary around a typical value, and the reason why you could get some of these variations, if you think about it, I had mentioned in a previous presentation that like oxide thickness in modern processes are down to the order of like 10 to 20 atoms in thickness. So if you think about even one atom difference in one transistor versus another could cause a 5% change in your T-ox thickness effective. So you can get variation even on devices that are right next to each other, but you tend to get more variation the farther devices are apart from each other, just due to various effects as you're going through and processing. And then of course from one wafer to another, you're going through all of the silicon processing techniques at different times, and so you will get different variation from wafer to wafer. This can cause you to sometimes have your NMOS device vary differently than your PMOS devices, depending on how the variation happens. So a couple different corners that are shown in the figure on the right there is, for example, if you had your NMOS device was slower than normal and your PMOS device was slower than normal, we call that an SS corner. Both devices are slower than typical, typical being the TT corner. The first letter is how fast or slow your NMOS device is. The second one is how fast or slow your PMOS device is in this case. So if you have an SF corner, it means you can have your NMOS device slower than normal, but your PMOS device faster than normal. And then of course there could be both of them faster than normal would be your FF corner, and your FS corner is a faster NMOS device and a slower PMOS device. So between all four of those corners, we now have kind of a bounding box around our typical corner. And if we do simulations at all 4, or actually all 5 corners, and everything to make sure everything works, we should work across all of the variation combinations that we can get in our processing. So let's talk a little bit about what happens to your parameters at the fast corner. At the fast corner, in order to be faster than normal, you want your L effective to be shorter, because a shorter gate length causes more current to go through the transistor. So L effective would be shorter than normal. Your threshold voltage, if you reduce threshold voltage, then your VGS minus VT parameter goes up. So smaller threshold voltage would be faster. And then Tox, as you reduce your oxide thickness, your electric field goes up and you attract more carriers to your channel, and so that causes more current. So a lower or thinner Tox causes a faster device. If you want the slow corner, you would do the opposite for each of those parameters. Now keep in mind, not all parameters are independent for NMOS and PMOS. Some of them, the NMOS is completely independent of PMOS, and some of them will track together. So just keep that in mind if you're trying to do some sort of process technology testing. So in addition to your process variation, we also keep in mind that there's environmental variation. So a couple of your environmental variables that you can think about are the voltage going into your chip, VDD, and also your temperature. Now those can vary over time as you're actually operating your integrated IC chip. Your VDD might have some amount of noise on it, and so it could go up and down. But it can also vary in space. In other words, as you supply your voltage to your IC chip, there could be areas where they're consuming a lot more current, and as they consume current, the voltage is going to dip in that area locally. And then in other areas, it's not dipped, and so you'll get some speed up or slow down of transistors based on that. So below we say we're trying to supply a typical voltage of 1.8 volts, and we assume that our typical temperature of our chip is 70 degrees C when it's in operation. So we might say, okay, if we want to do a fast environmental corner, that should be, for VDD, what would you expect? So you should expect higher voltage of VDD is going to be faster, and lower voltage is going to be slower. For temperature, I mentioned on a previous foil, as temperature goes up, your mobility goes down, so it gets slower. Temperature goes down, mobility tends to be a little bit higher for silicon, so it should get faster. So this gives us, potentially some additional corners that we want to stimulate, where we vary voltage and temperature, as well as the process variables of our transistors. And so we need to look at these voltage and temperature combinations as additional things that we might want to simulate in our SPICE sims. So we use what's called process corners to describe our worst case variation. And if the design works across all corners, or at least the outliers of all corners, it will probably work for any variations of process parameter differences that are in between those corners. And we can describe our corners using 3 letters, T, F, or S, typical, fast, or slow, over 4 different parameters. Those 4 different parameters are your NMOS speed, your PMOS speed, your voltage, and your temperature. So there's lots of variables there. Trying to do every combination of all 4. It's obviously a lot of simulations. Depending on how paranoid you are, you'll do more or less of those simulations to make sure that your device will work in all combinations. As I mentioned on the previous slide, our various different process and parameter variations have various different corners. So we have 4 different types of NMOS, PMOS, VDD, and temp, and we have 3 different variable or 3 different parameters for what type of fast versus slow versus typical, and so we have to decide what are the most critical simulation corners to do, because obviously you take these 12 different boxes here that are shown below and you try to figure out, okay, what are all the permutations of those 4 parameters and the 3 combinations of things we can put in there. We can get hundreds of simulations to do. So typically the most critical simulation corners to include, we want to see what is the fastest or slowest we can run our clock. So when we run our clock and we're trying to figure out how fast, like let's say a microprocessor can be, we want to do that at the slowest corner for all parameters. And if we can still meet our speed at that we require at that slowest corner, we should be able to meet our speed at any one of those being faster than the slow corner. Second thing is, for power, we want to make sure we don't come in over our power budget. So in this particular case, if we put everything at its fastest corner, typically that means it's going to consume the most current as well, and so be the highest power. So if we run everything at the fastest corner and measure our power, and that's within our budget, then we're good to go on power. And then finally, for sub-threshold leakage, that's something that when you aren't running everything, we want to make sure we're not consuming too much power just in leakage power when we try to turn everything off. And in that case, we want everything to be at the fast corner, except in this case for temperature at the slow corner. So that's just a couple parameters to keep in mind, and make sure that you can have an IC chip that is fully operational for all your usage conditions.